10:30. I think we can get started. I'll introduce myself briefly. I'm Willow Ahrens. I'm a student of Samans. Let's go with our first speaker, Charisse. I believe this is a pre-recorded talk. Okay.
a sparse graph like COM Amazon, the dense component dominates. And similarly, depending on the embedding sizes, the domination patterns also change. And also, like for CPUs compared to GPUs, the breakdowns are also different. So there is no one panacea or one technique that will work or that can exploit this observation to get better performance. Or more rather, we need some way to dynamically control the number of sparse and dense operations out there. So our solution to this was to use matrix reassociations. More specifically, given neural network computation, we will try out different matrix reassociations and we'll use the best according to the density of the graph. For example, if you take this graph convolution neural network computation, it has different dense matrices like D, H, W, and the adjacency matrix A is sparse. And based on how you reassociate, it can lead to different sparse dense components. If you reassociate from the right, this will result in 3 dense operations compared to 1 sparse operation. So this is more beneficial when the bottleneck is sparse. Whereas if you reassociate from the left, this will result in 2 sparse operations and 1 dense operation. So this is more beneficial when the bottleneck is dense. So now the goal is to automatically find these associations and select the best. To do that, we build this system known as Sensei, which consumes a graph neural network computation written in a message passing style, and its offline compilation stage consumes this representation, converts it to a matrix-based IR, and from that we follow a few steps to generate all possible semantically equivalent reassociations. And note that these semantically equivalent reassociations will result in different sparse and dense primitives. And then given these reassociations, we have a lightweight online stage that use pre-trained cost models, extremely lightweight, to decide which reassociation to use. So we implemented this on a baseline system, more specifically on DGL. And here I show you results for different graphs in the x-axis, and y-axis is the speed up, so the higher the better. And as you can see, in most cases, we were able to achieve good speed ups. And moreover, Sensei is not specific to a particular system. It's actually general across. It can be implemented in any graph neural network compiler. So we implemented it inside C star, and we got similar results. Okay. Now, next I will show you how you can build more domain-specific optimizations that will enable that actually enabled us to provide better abstractions for another sparse ML workload known as temporal graph neural networks. So graphs usually change. They are not static. For example, social network graphs, financial network graphs change across time. So these temporal graph neural networks are a special class of graph neural networks that actually processes graphs with time information embedded in them. So they are usually more computationally expensive than the static versions. And what we noticed was there was no good first class programming support for these networks. Most of the time, people will just use static graph neural network frameworks or would just use PyTorch to code them up. And this will result in a lot of missed opportunities for optimizations, as well as it may be difficult for the programmer to express these computations. So next we profiled, as with static graph neural networks, we profiled this one of the TGNN models known as temporal graph attention networks. And what we found out was majority of the time was not spent on sparse operations. It was actually spent on this attention computation. So then we build a system known as CGOpt that will reduce this attention computation significantly and getting speedups up to 6x, as shown in the right hand side. So you may notice maybe we have a better attention here. We definitely did not invent flash attention. So rather what we did was we found that most of the computations in these temporal graph neural networks have redundancies. So in TGOpt, we eliminated them using one key observation, that even though these graphs change, they do not change drastically. The changes are more incremental. So we came up with like three different optimizations: deduplication, memoization, precomputation, to optimize these workloads. So in this talk, I'll go into memoization a little bit. In order to motivate this, like let's look at the temporal neighborhood of a node V here, and assume that between timestamp T4 and T6 that I have shown you here, a new edge interaction comes up at timestamp T5. So the temporal neighborhood varies, but it varies only slightly. And in fact, most of the temporal neighborhood remains the same. So that means like maybe in the calculation of embeddings for V, we could use the embeddings of this same subgraphs. And this is not an isolated phenomenon. This is the most prevalent phenomenon across all timestamps. And in fact, if you look at this graph shown towards your right, the blue line shows that most of the embeddings can be reused across timestamps compared to being recomputed. So then we came up with a memoization technique to leverage this, which I'm not going to go to detail in this talk. So by doing memoization and the other two related optimizations, we were able to achieve significant speedups over a baseline implementation, sometimes achieving up to 6x. Okay, that's good. On both CPUs and GPUs. So that's hardware agnostic in this case. However, TGOpt was completely implemented by hand by one of my students, and it was hard to transfer the same benefits to different TGNN models. So to alleviate this issue, we came up with a framework with first-class support for these redundancy-aware optimizations targeting the TGNN workloads. So this framework known as TG-Lite has ready-to-use functions and domain-specific data structures specifically tailored to temporal graph neural networks, and also different optimization operators that can that the users can exploit to perform redundancy-aware optimization. TG-Lite is mainly powered by a data structure that we developed known as T-blocks. So these T blocks under the hood represents all the temporal dependencies, and moreover the way it represents these temporal dependencies is by building a mapping between target and neighbor nodes incrementally. So this incremental representation allows us to cache certain data items automatically. By doing that and coding up the different temporal graph neural networks in the TG-Lite framework, we were able to achieve significant performance improvements across different data sets. Here I show you two graphs. Here y-axis is the speed up, the average epoch time, and the x-axis is the different TGNN models out there. So as you can see, in most cases, we can achieve multiple fold performance improvements compared to TGL, which is a well-optimized programming framework for temporal graph neural networks. Okay. So with that, let me move to the last piece of the talk, which is about showing that sparse ML, you have to care about the moderate sparse matrices as well. So transform architectures power modern large language models. However, a significant portion of their computation goes to this attention computation, which is n squared. And here n means the sequence length or your prompt size. Or in a reasoning model, it can be like the number of tokens that get generated that get fed in again, right? So this can easily go beyond 100K or even 1 million these days. So sparsification is essential to achieve scalability in these workloads. And the way the researchers specify the full attention computation is as follows. In your left, I show you the full attention computation. We have the query key multiplication followed by softmax and then multiplication with the values. And in the sparse attention, you take the query key multiplication and then use a sparse mask to control which of these values to keep. So this is an SDDMM operation if you know about it. Right? And then you do the softmax and then the value computation. So maybe you can use an existing SDDMM library and SPMM library and it should be good. And however, what we notice is achieving good performance in sparse attention is very difficult. Actually, most of the libraries, if you use it, will result in a slowdown compared to using just dense. The reason is sparsity in sparse MHSA is moderate. And in sometimes the density is as high as 50%. So sparse libraries that are tuned for extreme sparsity may not work. Their metadata overhead is too high. That means we would need a more compressed format that is tailored to sparse attention to make it work. So this is where we came up with a new format known as sparse affine compressed sparse row. So key here is that we notice even though the sparsity is moderate, there's a lot of structure to this sparsity. And actually, the structure can be expressed as an affine equation. So rather than representing every non-zero individually in in affine compressed sparse row, we represent rows row by row using a few affine indices. So now we reduce the number of metadata overhead from order of number of non-zeros to order of number of rows. However, this doesn't solve the problem completely because developing format itself is not enough. You need to produce good code that will get you good performance. And this is where we develop this SPLAT framework, a novel GPU code generation framework for sparse attention workloads. And the SPAT works on ACSR matrices and it has provably minimal amount of tiles being created actually with good performance guarantees, and it has fast indexing schemes that we build and novel optimizations like span specialization and so on. And moreover, we implemented multiple different patterns using splat and it was able to optimize almost every one of them, so it is very general. So here I show you few results across a wide range of sparsity compared to NVIDIA's cuBLAS and cuSparse. And for three of these patterns, as you can see, the red line, which is flat, performs better up to a certain density level that we care about. And after that, of course, like cuBLAS is going to be better, but within the density levels that sparse attention care about, which is between 20 and 50% dense, Splat outperforms all of these hand-tuned libraries. And moreover, there are other handwritten libraries for these sparse attention workloads using TVM or Triton kernels. So Splat was also able to outperform these kernels. Yeah, here. Okay, in concluding my talk, I have shown you that optimizing sparse ML goes beyond optimizing just the sparse primitives. You need to think about compositions of different components like dense components, and you need to think about other domain-specific optimizations, and you need to think about the computation holistically. And finally, you need to also think about developing good code generation strategies for moderate sparse matrices, which is important. So with that, if you have any questions, unfortunately I can't answer them. I'll be hopefully in person on Tuesday, and I hope to see you all then. Thank you.
Up next will be Rohan. Rohan is a student at Stanford University studying under Fred Kostad and also works working with NVIDIA.
sure it's like my computer thinks that it's being plugged in. On me, I should have tried this earlier. Okay, I think this is working now. That's my email, don't look. Okay, sorry for the delay, but we'll get started. Let me just start my timer. Yeah, so thanks for the introduction, Willow. So my name is Rohan. I'm a fifth year PhD student at Stanford. I work with Alex Aiken and Fred Kjolstad. I'm also a part-time researcher at NVIDIA, where I work with Mike Bauer and Michael Garland. So I'm going to talk today about the system we built called Sparse that is going to hopefully make it easier for you to write sparse computations that run on clusters of GPUs and ML supercomputers. So on a single slide, well, what our system is, we build this set of libraries that basically enable you to scale SciPy sparse programs completely unmodified out to scale of supercomputers. So I have on the left some normal Python code. It's sequential. It looks like it's single-threaded. There's no distribution, communication, annotations in it or whatever. But you replace at the top of your program the SciPy sparse import with Sparse. You replace the NumPy import with CuPyNumeric, a distributed NumPy library we built. And this code, completely unmodified, is going to weak scale out from running on a single GPU, maybe storing a matrix of like 3.5 gigabytes, out to running at 192 GPUs of the Summit supercomputer. Just the code like this. And so this is really cool. There's a bunch of interesting things about this code. One thing I like to emphasize is this composition property kind of between the Sparse code and the CuPyNumeric code, where you can create some distributed data with CuPyNumeric. You can pass it into operators like this matrix vector multiply defined by Sparse, get some distributed data back out, and then pass it into CuPyNumeric with no real cost to that. You actually get composition like you often do on a sequential program. We built some pretty interesting programs in Sparse. I'm not going to spend too much time talking about them. You can talk to me later. But we built things like multi-grid solvers, which are commonly quite difficult to build in languages like MPI. We built the most interesting one was a simulation of some quantum phenomenon we built. And basically, the story is very similar, that you can write some pretty simple-looking NumPy and SciPy code and get code that actually utilizes a ton of GPUs on your big machine. So in this talk, I wanted to talk a little bit about building this library, which is really I think the most relevant component to this community. And so in 2019, Mike Bauer, my collaborator at NVIDIA, built this first version of this distributed NumPy called CuPyNumeric. And this started a big buzz within our group, and especially at NVIDIA. So I came in 2022 to try and start developing a companion sparse library to this distributed dense library. And we built a research prototype in 2023, by 2023, and a lot of it was focused on how do we build this sparse library, where all these kernels come from, and how do we actually enable this composition between this dense component and this sparse component. In 2024, people liked our prototype, so it got picked up by engineering. And actually, by the end of this year, Sparse has been released as an official product that you can actually download. I'll have some download links at the end of the talk. And we actually got some real customers. So people actually bought DGX machines to run the software, which is pretty cool. Our most interesting customer is a payments processor called NPCI. And what they basically use is they have these big transaction graphs created from looking at all their transactions, where there's an entry in this matrix, two people have sent money between each other. And they do a bunch of big SPGEMs on this to basically walk the transaction graph and try and find money laundering cases. And so, of course, a multi-GPU distributed program is going to go way faster than their CPU code. So they're very happy with that. More beyond Sparse, this work has also extended to building a sort of whole framework of composable libraries, where not just distributed NumPy and SciPy, we also have a bunch of things like distributed data frame processing libraries, tree boosting algorithms, and other machine learning things. And all these libraries have this nice composability property where they can import each other, use data created by each other, and this runtime system underneath them is responsible for making sure these programs run at the scale of a single GPU or all the way up to a larger supercomputer. So the actual technical challenges in this work, there are two main ones. And the first one, which is where I actually spend all my time these days doing work, is how do you structure runtime systems and these libraries to actually enable efficient composition between these libraries and actually achieve scale at the same time without costing you in performance. So I'm not going to talk about today. I'm happy to discuss offline at the conference. The part that is most relevant today, and also kind of a unique problem to Sparse, was how do we actually quickly build a library of these distributed sparse operations in a way that they're both high performance and they don't, you don't want to tear your hair out the whole time while writing all this low-level code. So to motivate the problem, and I'm sure this is a slide that many people have seen in many different ways, but so to build something like sci-fi, sci-fi sparse, it has a ton of different functions in that library, and of course all of them are defined over many different kinds of matrix formats. So you get this classic combinatorial explosion we've already seen a few times today, where you have a bunch of operations like matrix vector multiplies, matrix multiplies, and then you have a bunch of different formats you want to support that are all important. You have a bunch of backends you want to run the code on, like a single-threaded CPU, a multi-threaded CPU, a GPU. And then also in the distributed layer, you have another sort of addition to this cross product, where you may have multiple distributed algorithms for the same computation that you might want to choose based on the data, based on the structure of that sparse matrix or the context you're using it. And so in our case, we really wanted to get very high performance, so we want specialized kernels. It simply doesn't suffice to write one CSR SPMD and copy your data in and out of that format every time you want to do an SPMD. And so on a distributed machine especially, where the costs of moving data between nodes is very expensive, we really want to keep our data where it is as much as we can to make the code run as fast as possible. So to tackle this problem of actually building all the sparse kernels in our library, we leveraged this work that I did earlier in my PhD called Distal. And so Distal is a tensor compiler from the Taco family of work that basically you can write. It helps you develop distributed tensor contractions and actually run them on your cluster of machines. So like a lot of the other tensor compilers that we built, it takes in a notion of what you want to compute, something like an Einstein summation notation, just expression like Taco, and it also takes in a notion of how your data is compressed, this level-by-level description of your data formats. The interesting stuff in Distal, the new stuff is basically talking about how your computation is distributed, an algorithm that describes how you want to chop up this computation across all your nodes in your machine, as well as a notion of how you want to distribute your data. The way you place your data originally on this machine can differ from how it should move around during that computation. Distal takes in all these things and outputs you code that runs on a supercomputer. So I'm going to talk a little bit today about this, how we talk about data distribution, how we talk about computation distribution, and how we actually generate some of that distributed code used in that actually runs on this machine. So to talk about how you express the compiler, how you want to distribute your programs, well, there's just a few additions to a standard scheduling language like Taco that you might have seen. So you have your programs represent these nested loops. You have these Einstein summation notation expressions. And to talk about data distribution of computation, well, the most basic thing is you basically say, hey, I want a particular loop to be split across and run across all the different GPUs or nodes in my machine. And this transformation basically gives you out one of these loops that has been distributed. The other thing you need to do is control when communication occurs. And we have the way you tell the compiler this is that you say, I want to communicate a particular tensor in my program at a given level of my loop nest. And the basic way that you can imagine how this works is that what this is saying is that at every iteration of I want you to go figure out the data needed of this sparse or dense matrix at this particular loop nest, gather the data for me, and then actually run the computation that runs inside that loop nest. These transformations are sort of very simple. I think they're things you might expect to see if you're writing these programs. But the hard part really that is actually generating the code that does what the user is asking for. And there are two main things that make this really tricky for sparse programs, is that one, as we've seen before, these data structures are full of indirections. They're a bunch of arrays with scalars pointing into these other arrays. And then those indirections are also only dynamically known. You only know where these things point when you actually have the data in your sparse matrix. And many times we're not willing to specialize something just to a particular just sparse matrix. So to talk about how we get into this and some of the challenges, I just want to remind everyone about the CSR matrix representation, just so we're all on the same page. So CSR matrix, you have a collection of arrays, usually called pos, CRD, and vals. And the pos array has an entry per row in the matrix, and it basically represents a range of data in the CRD and values arrays corresponding to the data representing for each row. And of course, for each row, you have the data in CRD corresponds to the non-zero coordinate in that row and also the non-zero value. So, put this in mind. The main intuition for how a compiler like Distal works, I think this is if you want to remember one thing from the talk, it's probably this slide. And we exploit this intuition that the partitions you need to make of sparse tensors have static structure, meaning the relationships between all these arrays have a very static shape. Things like for CSR, it's defined in a certain way. But then the actual shapes that these partitions have is very data dependent. It depends on how the actual non-zero pattern of it looks. So here's that CSR matrix. I've chopped it up into pieces. So I've chopped it up into rows. And kind of for each row, I've colored all the data you need if you want to access the data for that row. And so when I say that these partitions have a static structure, I can write down a little program that represents the pieces of each array I need given a partition of one of these arrays. So for example, if I need to describe the pieces I need of CRD given a partition of the pos array, well, I can do that by kind of taking all of the entries of the pos array, unioning those ranges they have together, and I'd get out the corresponding pieces I need of the CRD array. So I can write down a little closed form program that represents this, but of course, I need the actual data at runtime to produce this thing. Another example is suppose I have a vector, I'm doing something like an SPMV, where I need to locate from CRD into this vector. Given a partition of CRD, well, I take all of the coordinates in CRD and I union all those together, and that would be the corresponding pieces of data I need in this vector class. So right, we have a static structure, but a very dynamic shape of these things. So our compiler exploits this intuition by basically defining a series of partitioning operators that are used to construct these structured partitions of these arrays. We have things like tilings, so you can take an array and break it up into equal pieces. This is not necessarily involves anything dynamic. But then we have these other operators that actually called dependent partitioning operators that perform some dynamic behavior here. So these arrays basically relate, these operators basically relate partitionings between two different arrays. So I have an image is defined that if I have like that pos-like array before that holds ranges into another array, an image is going to follow this indirection through. Right? If I have a partition of this source array, I get the corresponding, I partition it by following each range inside there and partitioning the destination in the same corresponding way as these ranges describe. And interestingly here, I sort of statically write down that here's my image, and then the actual value of it depends on what the sparse matrix data actually holds. And we're going to use a dynamic analysis when actually doing this thing in the compiler. We also have this kind of an inversion of the same image called the pre-image. We're given a partition of this array of coordinates or something. We can find the corresponding ranges that we would need to look at if we want to go the other way. So the way our compiler uses these partitioning operators is kind of through a format interface, which is the same way that many tensor compilers like Taco work today. So in compilers like Taco, there exists one compiler algorithm, and that compiler algorithm interacts with the different data formats through an abstract interface that the interface is defined kind of for each format that you might have in the program. So you have standard API calls that you maybe would say, the compiler is like, how do I get the range of this loop? Or how do I get a particular coordinate from my sparse matrix? And the format interface will return to you snippets of code that say, for the sparse format, here's how you do it. We extend this format, we extend this API with talking about partitioning operations, where individual formats will describe, say, hey, I made up of a few arrays. You should use a tiling to partition this array that I have, or you should use an image to partition this other array in this format. And so then we have one compiler algorithm that uses this API and dispatches to the right partitioning operators for each kind of format. To give you a very high-level idea of how this works, the compiler generates code by walking through the different levels in your sparse tensor and then outputting the corresponding code. So if you have something like an SPMV, the compiler generates code by asking each of the levels in the sparse tensor, how should they be partitioned, and then dispatches some code that actually runs on each individual GPU or CPU in your system, generated through a standard lowering procedure, something like Taco knows how to do. Okay, so I've given you a very high-level idea of this Distal compiler. So how do we actually use it when writing this Legate library? So we completed the initial version of this library around 12 weeks, which I think is really fast for what I pitched you, this distributed multi-GPU sparse library. And the reason why we were able to do so fast is because instead of, for every new operation, writing down a ton of CUDA code and corresponding partitioning logic and all the communication, we just write down a very compact schedule inside the Distal compiler. Distal goes and generates a ton of low-level code that we then lift into our corresponding API. And we were able to generate almost 50% of this library, 50% of the C++ or CUDA in the library, and around 10% of all the Python completely automatically. And the real important thing is that this is all the hard stuff in the library. Kind of the performance core set of kernels is all automatically generated, so you don't have to go spend time debugging them or manually optimizing them. It was kind of all done by this automatic process. So we could go and spend our time doing much more interesting things, like developing those cool applications I showed you at the beginning, or really stressing this composability aspect of the libraries. So one thing that was a bit unsatisfying to me that I think is definitely something you can do in the future is that I really like to see, rather than using distils ahead of compilers, we would like to use this compiler technology just in time, kind of keep it all inside the loop. And I think that we really need to improve our auto-scheduling frameworks to make this happen. I think, we've heard a bunch of talks. We've heard a talk today about auto-scheduling, and we'll hear some more talks by Willow about it. But I think that we yet don't quite have fast and reliable auto-scheduling, where fast meaning like in a millisecond or two come up with the schedule, and then reliable means I can kind of always trust it to do something reasonable. I think we're not quite there yet, and so for now we still need a human to come up with this schedule in our libraries, and we'll probably be stuck using them as ahead of time things for a while. But there's still a pretty big win in the productivity. Yeah, so Willow's going to talk about this stuff, but I think we made a ton of progress, especially now we're really good at getting the asymptotics of these sparse tensor contractions right. And once we have this, now we can then get some of these heuristics about when to parallelize things the right way, what tile size to use, and then we could actually have this compiler technology be just in time rather than ahead of time. So with that, I'm going to stop. I guess I thought that would be mostly a 15-minute talk, and so we were 20 minutes, so I went a bit slower. But I was telling you today that you can go download Sparse. The engineers work hard on this stuff, so I'm told that this con install actually gives you a multi-GPU, multi-node version of this package. So you can just con install and get the distributed version of the code right away. And I want to say that I think Sparse has been a result of a ton of progress that we, the Sparse compilation community, have been making over the last 10 years. This stuff has been going on for a while, and the compilers we built have enabled really rapid development of kind of difficult software. And so I think that that's a really big win for us in this room. So with that, I'll stop, and I guess we'll take questions during the panel. So thank you, everyone.
Thank you, Rohan. Does anybody?
Sure. Oh wait, I'm gonna start.
So up next will be Amir. Amir Shaika is a professor at the University of Edinburgh, and we will hear a talk about optimizing recursive sparse computations.
Thanks for the introduction. This is Amir Shaika. The correct pronunciation is Sheikha. You can call me Amir. This is joint work with Dan Sushio, Max Schleit, and Hong Go. So let's first start with the motivating question. So do we really need recursive computation whenever we are dealing with sparse data? So in particular, we want to see whether tensor algebra itself is sufficient or not. So let's take a look at the web tool provided by the Taco system. So here you can basically input your computation, and then the Taco platform is going to generate code for you. And this is basically the Einstein summation notation. However, if you look closely into it, it doesn't allow us to basically specify recursive computation. So here we have basically just summation and product computation on top of tensors. Uh, so let's take a step back. Let's look at the mission of the Sparse workshop. So in particular, these points. So perhaps this is going to be one of the only talk that we are going to cover this aspect of the Sparse workshop, relational algebra and graph processing. And inspired by that, now let's go beyond what the sparse tensor algebra is doing and see what is the opinion of the relational world on recursive computation. So for that, I'm going to use a quote by Mike Stonebreaker, one of the famous people in the database community who won the Turing Award in 2014. And let's see what he said about recursive computations in the context of databases. So he said that no practical applications of recursive query theory has been found to date. So this is a bit disappointing. But there is some hope there. This code was from 1998. So things have changed a lot. In particular, if you see the database world, there is a recent trend on graph query languages. And more recently, actually, you can see that even on the SQL standard, there has been some extensions to support graph patterns. So this makes us a bit more hopeful. Actually, this is kind of recent trend.
questions to start off this panel? You have a question.
So, distributed is hard because data, where data lives matters. So, how do you deal with throughout the computation to minimize the data movement? Especially if you're doing it with a very large chip. So, I think we should have another mic for the panel.
Yeah, so I think the question has two layers, like in terms of specifically for like individual sparse kernels, right? I mean, you want to pick with your scheduling, like you want to pick an initial duty and pick an algorithm such that you hopefully minimize this thing where you can pick algorithms that will, you can employ algorithms with like communication avoidance properties or stuff like that to minimize computation. I think the more interesting question is actually minimizing communication across library boundaries. And that part is much more in the runtime system work that we did. And I think the main intuition that I'll share there is about late binding. I think most communication happens at library boundaries due to early binding your program that a particular function, let's say, accepts data only in a particular layout. It accepts data in a row-based partitioning, and if that's baked in your code, which it often is, you can't do anything other than transform the data into the layout you're pointing to. So one thing that we do in our system is the runtime system allows individual computations to express their computation in a way that allows you to bind the partition quickly. So the key idea there is that operations in the library express things like, instead of partitioning, they express constraints. That say, I don't care how my partitioning is done for this particular tensor, but it has to satisfy this constraint. Like at least this dimension needs to be aligned with this one. And then that lets you actually later pick partitioning such that throughout the sequence of some operation, the partitioning can be repeated.
So, a quick question for Rohan. You mentioned in the talk a kind of this throwaway product called Digex or Digex. I'm not familiar with the space. So, what is that?
DGX is just anything to
DGX.
run. It's a DGX machine is like 8 server class GPUs in a single node. Like that's the unit of machining time for a single GPU.
DGX.
DGX Superfly.
So that's a product by which company?
NVIDIA.
Oh,
Yeah.
okay.
So like
Okay.
you buy a DGX H100, you can buy a H100. Yeah.
Okay. All right. Okay. All right. Thanks. Thanks for the clarification.
Thank you for your talks. I think my first question for Amir is for the recursive function for your work and also Fred's work that you mentioned at the end, how does it connect to Silk? Because we had this cache oblivious compiler that actually do the recursive. They don't actually make it on recursive as far as I remember. So how does actually your work is like? How is your work is different, or how can Silk benefit from that, or your work benefit from Silk?
So to be honest with you, I don't know the detail of Silk. So one thing that I can say from a very high level point of view, the type of recursion that we are handling, I would say is more general recursion. So from my understanding, basically the recursion that on Fred's work, it's very much centered around still loop indices. So the type of recursion that we support is not really dependent on that. It could support that one, but also it goes beyond that. So my understanding is that whenever you have loop indices, you can do much better data dependency analysis. Whereas in the more general world, you don't have that information that much. So I would say that you can generate more specialized code in these cases.
I see. No, for the Silk, actually, what I think what happens is just keep it as a recursive work and just like trying to feed it into the cache by recursion. So if you basically keep it as a recursion, that may be reasonable backend to just use it as a separate code. But if you remove the recursion and make it like a non-recursive, then I don't think that's just different, I guess.
Yeah. So one thing that I have to say is that so if you're basically considering not doing your reasoning beyond the recursion boundary. So you're basically just optimizing the kernel that is inside the recursive computation. So one advantage of the work that I presented was that it uses logics, and based on the logic, it can do some sort of global way of rewriting across the boundary of recursion. So in the data log world in particular, the keywords that we can look into is one very interesting optimization is called magic set optimization, which was generalized, I think, 2 years ago or 3 years ago to FGH. That's the name of the rule. Yeah, I'm just giving the keywords for that. So one interesting thing that you can do is that you can do a kind of more general version of loop invariant code motion across the recursion.
Does anybody have any other questions?
Hi, I have a follow-up question for Amir. So yeah, I'm wondering. So you are So I think you are using the recursive or recurrence relationship to reflect it downwards to the translate for the code generation. So so are you thinking about is there maybe any potentials that we can reflect the recursive relationship in the notation? So by extending some of the notation, I'm just wondering.
Can you give me an example?
Oh, well, so you mentioned like, so Einstein notation, we cannot reflect the recursive. So is there any extension to Einstein notation or anywhere like?
Oh yeah, so
Yeah.
so the data log, if you think of it,
Yeah.
it's basically using Einstein summation
Uh-huh.
notation. However, the normal data log is basically the sums and product is over the Boolean semiring. So there is extension of data log called data logo, which basically generalizes it to a larger subset of semirings, which are called pre-ordered semirings.
I see.
And so the extension that they have is usually with Einstein summation notation, the head relation, the left-hand side relation, is different than the right-hand side relations. So whereas in this data log and data logo notation, you can have reuse of that. So there is a recursion there.
Oh, okay.
Yeah.
I see.
And even more interesting, you can have a set of mutually recursive definitions, and then you can basically define A in the first one and use A in the second one, define B and reuse B in the first one.
Yeah.
You can basically go crazy with that.
So I see. Yeah. So that's awesome. So then, that's in the programming level or the notation level. So programming level, right?
Yes.
I see.
So it's a declarative language. So the declarative language very much like is very similar to the Einstein summation notation. So one thing is that Einstein summation notation also could be generalized to other types of semirings like this min max and those kind of semirings.
Right.
So this is how, for example, they also can express shortest path. For example, data logo, not data log. With data log, we cannot do that.
Oh, I see.
With a pure data log, you need to extend it with aggregations.
Okay. Thank you so much.
Are there any other questions?
Rohan, I have a question. So I personally work on the single node. I saw you working on distributed. One question that I have, like, because we are working, when you talk about the communication data movement in single node, is pretty much locality. And in a sparse code, we always, at least in my papers, we always improve locality. So what is the big difference between the locality improvement and communication reduction that actually in the context of distributed? Is it like just the cost of communication that is higher, or is there any other major difference?
I mean, the cost of communication is higher. I think the fundamental thing, though, is often when writing these programs, like, difference on a single node is that if you miss your cache, you will still get the data. Like, you can still just issue a load and you'll get the data. But in a distributed setting, there are kind of unified addressing things with these machines, but oftentimes, if you access data that's not on your node, you can't get it, right? You need to actually go ask the person who owns it to give it to you. And maintaining that, like finding out where it is, or and then actually doing the communication in a way that is efficient to get it to you, doing it in a way such that maybe you're doing some other useful computation while the data is flying towards you. These are all things that are different in kind of the distributed setting.
I see. So the second major difference is just the way you insert the communication primitives into your code to make the memory consistent.
Yeah, and so you have to figure, that often means your code needs to understand for any piece of data, who has this data, how should I get it to me, and is somebody going to update this data before it gets to me? Like, these are the questions that start to matter.
I see. But I think from the presentation, I saw that your focus is like in the second part, like the communication primitive is not like really on the scheduling and improving, like reducing the communication, or is it both?
I think it's both. So I was just saying to Saman, reducing the communication is something that within your individual algorithm you control. And then I think the second part is often the glue between different components of the code that need to, one part of the code uses some data in some orientation, and the next part of the code needs to move it around so the next piece of the program can then use it successfully.
And when you're talking about you mentioned multi-GPU as well. So I know that the communication fusion, like the actual computation in the GPU communication primitives is also common, like for example, a nickel primitive with some sort of a computation. Are you also handling those in legacy Sparse, or?
Well, I think to tease that out a little bit, right? I think more of what we do is that in a multi-GPU machine, there's a lot of hierarchy in the communication channels, so that whenever you're moving some data, there's a particular channel you need to use. Like between nodes, you need to use GPU direct. Between GPUs on the same node, you need to use the NVLink, and then like similarly for other things. And so, we dispatch to the right ones to move the data for the appropriate things, and that means, for example, on like a multi-GPU machine, you might have to first move some data to some buffer with GPU direct, and then move it again, like that sort of stuff that we deal with. I think the communication fusing that you're seeing today in a lot of ML kernels is instead tackling a different problem, where basically the latencies that they have to deal with are so small that they need to basically do the computation in a particular loop of an MMA while the next one is being loaded. Like the latency is too small to launch a kernel and then do the communication and launch another kernel.
Are there any remaining questions? I can ask one. Amir, how would you describe the relationship between your system and sparse formats? For those of us who are maybe looking at this and wondering, okay, how does this relate to CSR? How does this relate to these kinds of data structures?
Yeah. So I would say that this particular work that I presented, it's I was focusing more on the higher level of the abstractions, mostly dealing with logical optimizations. I would say whenever you want to deal with the data formats, those are more what I would call physical optimizations. So one thing that I didn't show here was lower down the stack. So I've shown free data log, then there was tempo DL. Below that, there was a lot of things that I didn't show you. In particular, I was using an intermediate language called SDQL, where at that layer, actually, we deal with sparse data layouts. But for the experiments that I've shown here, we were basically mostly using a data layout that is very similar to COO. To be honest with you, it's not COO even, because COO in the database terminology, it corresponds to column stores, and the representation that I'm using here is actually a row store. So it is similar to COO, but it is not COO.
Thank you. Yeah, so it would be fair to characterize it then as like at some point after the optimizations, you're running a regular sparse compiler on the
Exactly.
on these.
So that's perhaps very connected to your upcoming paper, Galley. Is it upcoming? Yes. Yeah. So basically, there is a lot of things that needs to happen after that. In particular, one of the things that we have to do, which is similar to the question that you asked Kazem, which is actually for the operator reordering, that is something that at the physical level we have to do, along with the choice for the data format. So for example, similar to the choice of matrix multiplication, which multiplication to do first. So here also to join two relations, we have to make do similar choices.
I see.
Yeah.
I actually have a question for Rohan as well. So it's almost a similar spirit of question, but what's the relationship between your system that you were talking about here, and then the underlying, like, I don't know if it's a compiler infrastructure or is it just standard Sparse calls, or like the implementations of the kernels that are running locally, and is your system generating different versions of those?
Yeah, so the initial version of the compiler itself kind of does everything. Like, it just generates the loop nest all the way down. And then when we actually built this, at the time, KuSparse has improved, even over the last 5 years, KuSparse has improved a lot. And so the kernels that we were just generating better code for has changed. So at the beginning, we actually just generated all the code ourselves. And then certain things like SPMM or SPDNM have improved over the years, so we switched over to those things. But those often are like local changes. The distributed algorithm itself is the same, and then you swap out the kernel running on your individual GPU for KuSparse. We found that for a lot of things, though, when you have to deal with this distributed thing, it's hard to trick KuSparse sometimes into doing what you actually want it to do. Like, you have some weirdly sliced piece of data representing the local part of the CSR or whatever, and then KuSparse sometimes can get very unhappy with it was not built for this particular use case where you're like operating on some part of a bigger data structure. So for some of those things, we would like to use KuSparse, but we can't because it doesn't interoperate well with the kind of code we want it to.
I see. Thank you. Well, everybody, you can thank our speakers. I think this is the end of the panel. And it's lunch now, right? All right. Thank you, everyone.
테스팅. 아웃. 이거 왜 다 줄여져 있지? 테스팅. 테스팅. 하나 둘. 하나 둘. 테스팅. 테스팅. 하나 둘. 이게 줄여져 있었습니다. 맞아. 이게 아예 닫혀 있었어요. 그거 완전 엄청 작게 들어갔을 거예요. 제가 여기서 올릴 테니까 여기서는 안 올리셔도 됩니다. 테스팅. 지금은 충분히 하실 것 같아요. 너무 세게 들어가시는 것 같아요. 아까 이렇게 돼 있었거든요. 지금 제가 조금만 올려도 커지거든요. 너무 클 겁니다, 소리가. 맞아요. 근데 여기서 줄이셔야 될 것 같습니다. 여기. 아마 풀로 거의 풀로 되신 거예요. 아웃 얘기하시는 거랑. 지금 한 12시? 네네. 테스팅 하나 둘 하나 둘 하나 둘. 테스팅 하나 둘. 더 줄이셔도 될 것 같은데. 테스팅 하나 둘 하나 둘 하나 둘. 테스팅 하나 둘 하나 둘. 테스팅 마이크로 시험 중입니다. 하나 둘. 테스팅 하나 둘. 테스팅. 테스팅 마이크로 시험 중. 괜찮으신가요? 오케이. 테스팅 마이크로 시험 중입니다. 이거를 저희가 이렇게 조절해놨는데 누군가 줄이신 것 같습니다.
Sorry, so this
This one.
someone was apparently like
Out.
that all the way
Out.
down. Okay. Increasing it on the top. I think solved the problem. This one is for
메인 아웃.
main out.
Yes.
So that's the one that goes in here. This one.
Yes.
Yes, this one was too low.
Yes.
Okay. Oh, great. Yes, that's awesome. Okay. Thank you so much.
한 번만 해봐.
하나
And so today, so first, Hamira and Mateus are going to give a talk about PyData Sparse and integrating with the Finch compiler.
Okay, so we can start. I'm connected. Okay.
structure of the product of two diagonal matrices. So we take those structures an input, and we can simply guess that the output will be a diagonal matrix again. And we can do that in general for all those structures we include. Now, seeing that, we realize we can do more than just this sparsity reasoning. We can work with redundancy in that context. And so let's see how we encode that with a simple symmetric matrix here. You can notice we have two sets of indices now. We have the same bounds as before. And more importantly, we have here a transpose-like expression of those indices. This is to signify that we know those transpose element will hold the same value at runtime, whichever the value. And this transposes the definition of the matrix symmetry, right? From that information, what we can infer is a smaller set of the values we do need to compute, because we know that if we want to recover one of those lower values, we can get it from above. So we get this per diagonal subset in this example, which gets expressed as a unique set, which can get further propagated to look for further benefits anywhere else in the program. To clarify, this is not limited to known structures as diagonals and symmetries. It's just those basic examples to show you this encoding, but it can work with pretty complex structures, as this one arising from the covariance matrix showing up in polynomial regression degree 2 as an example. But you can observe that it's starting to get more complex, and this framework is able to completely reason about that and leverage it. To see the kind of results we get over that, simply inferring this structure and generating code iterating over this subset of elements we do want to compute, we observed already orders of magnitude of speedups. So we get this complexity objective we wanted. We get scalability too. We can see the benefits keep scaling with the size of the problem because the sparsity keeps increasing, just like with this code iteration in the sparse frameworks. So we're super happy about those initial results. But at this point, we look at what remains, right? So this is the example of a code that struct tensor could generate for a diagonal matrix product. It achieves, again, this complexity scalability goals by generating one single loop that is iterating over this output unique set here and simply doing those computation on the necessary subset. Now, if we look at this instruction side for now, we can see that this still works with the old full matrix encoding here. We actually get elements of multidimensional arrays. So we don't get any storage benefits. The cache locality is completely is so bad because every time you will need to load the full line, yeah. It's pretty awful for the vectorization too. We get those huge strides between H elements despite their simple structure, and struct tensor did not deal with parallelization of the kernel so far. So here are the remaining goals. We start looking at the storage, first of all. And we think we have a pretty geometric representation of our sets already. One great formalism to work with those representations is the polyhedral analysis framework. It simply asks us to have only a wide generalization of affine expressions in our encodings, which we found to be no bother in all the studied cases. In return, we get the capacity to simply compute a linear index for each of those elements, which would be a great solution, right? We now have a function that returns us one unique index for each element of this subset rather than the whole matrix, which is just what we need to index them in a very efficient contiguous buffer containing only those values and none of the upper triangular we don't use here in this example. The polyhedral framework also contains utilities to generate those loops, just like struct tensor did with advanced branches, which is great. Yeah. So with this indexing, we can now simply plug this indexed compressed buffer in the computation. We know we're only iterating over those indexed elements. So it's as simple as putting it here. What it gives us is the storage benefits. We can now work with this simple diagonal only layout of those elements. Of course, it helps with the cache locality. There's no zeros to load and store in those caches anymore, and the vectorization is only improved because those elements are fully contiguous now. Now, this indexing even provides a degree of freedom in the order in which you define those elements. So DASTAC does use that to index them whenever possible in the very order we iterate over it to completely maximize this vectorization. This compression on top of the previous structure inference benefits stacks up from like five speedups on the very same problem. So this is only embedding this compression on top of the previous iteration style. On top of that, as mentioned, the polyhedral model can generate loops for us. So it's pretty mature and able to generate parallel loops too pretty easily for those restricted computations. So we used a very naive first draft way of parallelizing those computations. As in, it's not very specialized on that part yet, but we observe already a capability to scale pretty much as good as the best competitors on that criteria we had, which was PyTorch on this occasion. So we celebrate, we checked all our boxes. We get all the benefits from the sparse world, from the dense world, on those cases where we have those elegant knowledge to leverage, and all is good. So what's left for us to look at? That's where I want to go now. Concretely, struct tensor, then forwarding to DASTAC, does demonstrate the huge potential of this way to compile those problems, but it does so with a very specific DSLs, just carrying this computation we're looking at and those general noun structures. So it was great to experiment and demonstrate all that, but I do think it will limit any kind of real-world impact this might have the potential of. So a first thing we want to look deeper in is more general structured computations, more general than simply addition and multiplication based tensor contractions. Here's an example from the AI world where they do use in attention layers the softmax functions, which ultimately boils down to summing exponents of elements of those tensors, here I as the input. To encode some relationships between those informations, they very commonly use very structured masks. Those masks are specialized to this exponential, such as you just add a simple mask to your input as a way to enforce some ignored element in the exponential. That is, this mask is based on zeros and minus infinities, so that the minus infinities in this case do collapse to minus infinity when added to the input, getting zero on the output, and the zero leave the output unchanged in this case. So we do feel like this could be reasoned in very similar terms with, right? It's just the formalism wasn't done this way so far, so I'd like to explore that to be able to use it in all those cases. More generally, I think the DSL approach is a limitation for the impact because the way I see it, structure is not a domain at all. It just naturally emerges in so many domains. So I do believe that what we want in some infrastructure in such ways that different domains, for example, probabilistic programming exposes a lot of structure in its discrete probability distributions. All of those, quantum simulation can be translated pretty easily to just combination of gates represented as small but very structured matrices, perfect candidate for this optimization framework. So they all have their different DSLs and specific optimizations already. But what I think such an infrastructure could help with is then translate them to this common representation and allowing even further co-optimization of those kernels beyond so widely different initial formalisms. So I'm pretty excited about that. And then it lets us imagine co-optimization between any kind of specific domains displaying such structures. There is initial work already on recovering structure from static, that is compile time known tensors. It's a hard problem, but we're interested in exploring how this could potentially help co-optimization with those fields. And yeah, those static tensors are widely present in AI at the inference stage where the model is trained. And those weights are just huge tensors that we statically know. So we could have a lot of time to reconstruct this structure. Finally, I don't think structured tensors are the silver bullet, right? We will need sparse layouts for a while. So I do think it's necessary to think about interoperability. I don't want those two point of views to compete against the users. I want them to collaborate to give the best benefits to everybody. And that could be a great fallback for those complicated tensors. Finally, if we want concrete application, of course, we want more serious targets. Right now, this is heavily experimented on top of CPUs, and we do want to leverage those GPUs or distributed memory systems to bring it down. So here are a few of the leads we are planning to explore as much as we can in the following years. Here are the title of the two mentioned articles. For those who would like to read more, my email address, feel free to drop me a mail and I'll be available as much as possible on the PLDI Discord. Thank you so much. Enjoy the rest of the workshop and hopefully see you soon.
While she's setting up, our last speaker today is going to be Willow. Willow's a postdoc with Saman at MIT and an incoming professor at Georgia Tech. They're just going to talk about auto-scheduling stuff today, I think, right? All right.
One more time. Testing, 1, 2, 3. Cool. I believe I've plugged in the laptop. Oh, great. Okay. Yeah, so thank you everybody for giving me the opportunity to come here and share this work with you today. This is some work that was led by Kyle Deeds. Kyle's a student at the University of Washington, working under Dan Suchu. And Kyle, his background is a little bit more in like databases and cardinality estimation. So Kyle does like theoretical work on cardinality estimation. So Kyle reached out to me a couple years ago after he read a paper about like asymptotic auto-scheduling that was a PLDI'25. And he said, hey, this database stuff is something that we should really look into for sparse tensors. And so now we will talk a little bit about the system that Kyle built as a result. So this is my slide. I'm obsessed with array programming. I start every talk with a slide about how much array programming has changed our world, and it kind of changes how we think about programming with collections of data. We're all using NumPy and TensorFlow to write machine learning models and scientific simulations and all of this stuff, and it makes it easy to do. A lot of these systems are optimized for dense tensors, and one of the reasons for that is, this is sort of, Rohan mentioned the kind of enumerative slide that we all have. I'll take a different take on this slide, but we have to fuse our operations together with sparse computing, which means that each operation needs to be treated separately. We also have this issue that we're going to do many different sparse formats, right? We have different kinds of structures beyond sparsity. Maybe there's blocks, or you might do things that are like not quite sparse, like run length encoding or symmetry. And then, of course, we have many different like ways that we'd like to execute this kernel, different schedules. So you could do, different traversal orders, or run it on a GPU, or here we want to do some blocking and tiling. So, of course, we know that this is too many kernels to implement by hand, and we need to use a compiler. I would argue that in this, room, a lot of the solutions that we've generated have solved these 4 horsemen of this apocalypse. So we have like collectives. We saw in the previous talk where we have a lot of really interesting interfaces to make it easy to program with these tensor compilers and specify particular kernels. We also have these hierarchical descriptions of data structures, right? Whether using hash tables or lists, we can describe a sparse tensor as a tree, and we have a lot of compilers that are really good at mapping these tree-like structures to efficient code. Of course, we can change the kind of data structure we use at every level. So there's a lot of parameterization going on. We can adapt this concept to handle different kinds of structure that we might see. And then, of course, we have scheduling commands, right? This was a really big innovation in performance engineering because it makes it a little easier to write transformations on the code without having to do all of the heavy lifting yourself. And it allows you to make sure that the idea is that these commands will reorganize the code after you've already said what you want to kind of tell you how to compute it. And of course, you might also think of this in terms of like kind of describing the data flow at a high level, right? And then you can adapt that to the structure. This is too many options. This is a really big slide. This is a lot of custom, very like specialized knobs and bells and whistles that people who are programming these things have to actually learn in order to use the tensor compilers effectively. And so the situation that we get, right, is that we have our domain expert. We want to do some Python on our data, and the structured code is really complex. We have all of these choices. And so we ask a performance engineer to do it, right? And now the performance engineer is writing the schedule. And so at some level, these scheduling languages are a really great marketing innovation to talk about like how to say that the interface is really here, but the schedule is going to be down here. And so in some ways, I would argue that if the last human in the loop is at the level of the scheduling interface, then really this is the interface, right, and not the high level thing. And so I think really like in order, so another caveat here that makes everything worse, right, is that the performance also depends on the sparsity pattern. So we need to draw a little line here, which means that now we're asking our performance engineer to do different specializations for different data sets, just adding on to the problem. So if we really want to claim that our interfaces are at this high level, then I think that we should, everything beneath the interface should be automatic. So to give an example of why the performance depends on the sparsity pattern of the inputs, consider a sparse matrix vector multiply here, where we're multiplying with this sparse vector. You can do this 2 ways. If you do this in a row major order, you see that we kind of have to traverse both of these lists, and when the 2 lists don't share a non-zero at the same location, that traversal is kind of wasted. We're checking if the other one has an element, but we're not actually doing them all. And so here you can see the row major traversal is doing a lot of checking and not very much multiplying. One thing we like about row major traversals, though, is that it's output stationary, which can be a big deal if you're parallelizing or something like that. So the column major traversal is like asymptotically better. We can check based on the vector x whether we actually need to traverse the column at all, which is a huge improvement. So here we see the difference between the two. So as we're making our decisions about cost modeling, it really, what we need to do is come up with a way to model the cost of the actual matrix as it relates to the computation. So we'll take an example of like a matrix multiply with two sparse matrices. Here's our example loop order. So this is the Gustafson's algorithm for matrix multiply. And here's our two example tensors. They're in a tree. A is a very complicated tree, and B is a very simple one. But we're not going to worry too much about the structure of B here. So here, in our loop over I, we're going to be looping over these edges. And then in our loop over K, we're aligning these two vectors, right? This is that same problem we just saw in the sparse matrix, sparse vector case. So here we see that the two values of K are shared, and so we should traverse this element J. Here we see, the first entry in the row of A is 2, and so then, of course, they have that shared entry, and we need to do the multiplication. But in this other case, if it's 3, they don't match, and so we don't do the mul. And so if we were to add a cost, we might say that this I loop is going to iterate once for every non-zero row of A. The K loop iterates once for every entry of A. And then the J loop is going to iterate once for every non-zero in this three-dimensional object that I've sketched here. So this is a really simple way to talk about the costs of this algorithm. And so we could actually compute these things and figure out what the cost would be. Of course, actually running the algorithm is expensive, and we need to do a lot of different, as I said before, there's this combinatorial explosion of all these different choices we need to make, and so we need to be able to model the cost efficiently. So this is where the database literature starts coming in. We can draw an analogy to cardinality estimation. So cardinality estimation is just estimating the size of a join in a database world. But there's a couple differences. One is that dimensions are finite domains, right? So in the database world, we have these infinite attribute domains. Here they're finite. Another is that aggregates are really common in the sparsity world. This is something Amir was pointing out. And selections are uncommon. And so we chose to use degree sequence bounds. This is also like a bound that I think Kyle is very fond of. And so the idea here is that it's a distribution over the occupancy of the matrix. So you're essentially asking, how many rows are there of length 1? How many rows are there with 2 non-zeros in them? How many rows with 3 non-zeros? And you can use this histogram as kind of like a way to estimate the sparsity of certain outputs. In particular, this gives us an upper bound on certain sparsities, which is useful to us because it's safe. So we don't make decisions that are, catastrophic. But you might choose other cardinality estimation. There's many different estimators that you can choose. So how do we build this into an optimizer? We have, you can kind of think of auto schedulers as having you need a search space, you need a cost function, and then you need a search strategy, right? Now we're in the search strategy part of this. So we have our input program. It's in our NumPy. We'll pass this to a logical optimizer, which results in this logical plan. At this stage, we're just choosing which kernels should be fused together and which ones happen separately. Then we pass it through a physical optimizer. This is making decisions about what the loop ordering should be, what formats we want to use for intermediates or for the outputs. And then we pass it to a sparse tensor compiler. And of course, the sparsity estimator is based on the inputs, the sparsity estimator is going to use the inputs to inform these two stages of optimization. I'm sorry, is that me? Oh, okay. I'm going to keep going. Anyways, you can see this talk about, I can talk more about Finch. We have a paper at OOPSLA, so if you want to see more about that, it's a talk I've given many times already, so you can go to Singapore to see that, and we'll skip that for now. Let's talk about Galley's logical optimizer. So the problem is that optimizing join ordering and aggregation simultaneously is a huge search space, right? It's hard to choose all these fusion optimizations by just some enumerative search. So our solution here is the same solution as in databases. We'll use variable elimination. So the idea is that an elimination is we will pick a particular index that's in the sum, and then we'll sum over that index, and that leads to an intermediate tensor. So the idea is that if you choose the order in which you want to do these sums, that's the main fusion decision that you're making about which tensors need to be processed together. And so focusing solely on this, like, index by index approach really reduces the search space. And of course we'll do, we still have like an n factorial number of orders, and so we can do a little bit of dynamic programming and stuff like that to reduce it. But the key idea is that this elimination order implies a fusion plan. So to give a little example of what this might look like, we have our classic matrix chain multiplication, and we can represent this with a little expression tree. So here's our summation over j and k, and then we're going to do the pointwise mole over all of these. So this pointwise mole is like, you can think of it conceptually as producing a 4-dimensional object here, because there's 4 distinct indices. But if we do a jk ordering where we sum j first, we see that j is touching a and b, but not c, and so a and b are involved in this elimination, and then k is involved in the subsequent elimination. That leads to a plan like this. Of course, you could do the other way, and it would lead to a different plan. This leads to a little bit of a question, because I've been moving these summations around, and not everything is summation. We just had this excellent talk from Hamir and Mateus about all of the different array API operations that we want to support with a system like this. So we get really specific about which algebraic properties we're using to push aggregates down the tree. So in particular, we need to use distributivity to do some of this, and commutativity as well. So certain algebraic properties might restrict the elimination orders that are available to us as we do this search. So we're kind of pushing the aggregations down as much as we can, subject to the algebraic properties that we're working with. Then of course we hit a physical optimizer, and these sort of concerns may be more familiar, where we're talking about optimizing a loop order. The general idea is that you want to lift the filters higher in the loop nest, but we can of course use a similar dynamic programming over the orders, and then of course we have to pick formats. And the nice thing about using sparsity estimation is that we can use it again here to estimate what the actual cost would be in any given format that we're choosing. So we choose among 4 different level formats that we found were sufficient to cover most of the use cases. And they have a couple different properties. So the bitmap and the dense one store a full dense representation. The bitmap is unique in that it allows you to do a traversal over just the sparse elements, where a dense representation wouldn't even allow you to do that. And then of course we have hash tables and sorted lists, depending on whether or not we need random access in the case that we really truly want to have a format that is O of n and z rather than O of n. And then of course we have the issue of intersection algorithms. Because Kyle is from the database world, we'll take a database-inspired approach here, and we'll do the iterate lookup strategy. We have a sparsity estimator, and so it can tell us whichever one is smaller. So in this case, this is actually the bad choice. We'd probably want to iterate over B first and look up into A. But the idea is that you can just pick one of them as the leader and then look up into the follower. So we have a little bit of results here. We use, so we're focusing on subgraph counting for our experiment. The idea here is that we're going to count the occurrences of a graph within another graph. And it's equivalent to taking a product of the graph matrix with itself, enough times to represent the small query object. So this is where we get triangle counting is really just a map mole of 3 matrices. If you want to count something other than triangles, then it looks like a different matrix chain multiplication where the indices are shared in various ways. And so there's a couple standard data sets and queries based on this, but we think it's a good test of an auto-scheduler because it really has a lot of variance in the kind of kernels that we're testing against. And we see that we're competitive with state-of-the-art database optimizers like DuckDB. Of course, one interesting thing that we can see in some of these plots is, as you might also ask what the execution time would be if we used a different backend. So how much of this is like the execution engine, or like Finch versus DuckDB's vectorized executor, and how much of this is actually like the sparse compiler point of this. And we see in certain data sets that using a sparse compiler is actually helping us quite a bit, whereas in other data sets the difference is less so. I'm going to skip this one. Anyways, we also, for a more familiar comparison, we did a little bit of matrix chain multiplication on a pathological example with PyTorch's sparse matrix multiply. And so in this case, C is super sparse, but A and B are more dense. And you can see that as C gets sparser, the performance of PyTorch is staying the same. It's doing the same, multiplying the two dense matrices first, and then, so it has the wrong order. Interestingly, if you swap the order, you would think that PyTorch would start to do better, and it does, but it doesn't quite match the performance. I believe this is because it doesn't have a doubly compressed format that it's choosing to use. So at some point, we realized that indeed we should also start compressing the rows in addition to the columns, like the DCSR. So that's our hypothesis for this one. And then this is an example where we do a matrix chain multiplication, where I believe that this is related to whether you really need to materialize anything at all in this. So yeah, in conclusion, I think that sparse auto-scheduling is both necessary and achievable. We've written some great tensor compilers, and I think we can also write code that knows how to drive them. Existing tensor compilers have a lot of complex bells and whistles that make it hard for the average user to use them without knowing how they really work. But an auto-scheduler like Galley can get us to this usability that I think we're all hoping for. There's a little archive QR code. Thank you for your time.
Okay, we'll get started with our panel. So everyone who gave a talk, please come to the front. One of you might have to bring your own chair. Do you know if Emilian is trying to join on Zoom?
I think he's trying to. So just give us a second.
Yeah.
Just leave this here.
Let's give it a minute or two, and then we can start with the structure. Let's see. Oh, sounds like it's working. Sounds like it's about to work. Hey, Emilian, can you hear us?
Hey, yes, I can. Can you?
Yep, we can hear you. Okay, so we'll start the Q&A. I'll start with a quick question for Willow, and then we can pass it off. So I appreciate the connection, like the Galley optimizer is written out very much like a normal database optimizer. I'm wondering where statistics come in, because that's kind of the main reason these things work in the first place.
We have extra mic for them?
Yes. I guess I was just holding the mic. I was waiting for someone to start.
Give them that mic. So Willow has that mic. He can use that mic.
Is your question where the sparsity estimation comes into the optimizer?
Yeah,
Yeah.
Where did the original statistics of the underlying data come in?
Yeah, so it's used to, So the cost model for fusion, where we're doing the initial variable elimination in the logical plan, is estimating both the size of the output, so it's using sparse estimation to do that, and then it's also estimating the estimated number of computations that you'll need to do, like bulk computation, in order to make decisions about what to fuse. So that's like phase one cost model, right? And then the finer grained cost model, when we're talking about loop ordering, it's using a very similar loop ordering model to the PLDI paper about asymptotic autotuning, where we think of the sparse loop as a filter, and then you can have like a recursive algorithm to estimate the sparsity of, I guess, the sparsity of each loop. How many times each loop runs would be the estimate there. And then for estimating the formats, we know that we only need to store a child or a parent node if any of its children are stored, and so this leads to another, very similar few sparsity queries. Does that answer your question? Okay.
Any other questions right now?
Yeah. So actually, I have one comment and one question. So one comment was, so if I understood Finch correctly, you're basically doing code generation at the end. Am I right? You're basically generating. You're not interpreting.
That's right. Yeah. So we compile a custom kernel for each input.
Yeah. So one comment is that perhaps your competitor needs to be changed, because DuckDB is an interpreter-based database system. So you have to use some database system like Hyper or Umbra, which are also code generation based, and that's going to make it more fair comparison.
Yeah, I mean, you could see in the plot that, like, if we change the backend, right? Like, DuckDB was actually making okay decisions. It's just that, like, we needed to use a sparse tensor compiler, which maybe makes me think DuckDB should be using a sparse tensor compiler rather than us using a DuckDB optimizer. But I don't know if that's the takeaway that you want to have. But that's a good point. Yeah. I wonder also if there's like sparse auto-tuners that should be compared against too. If it were, I mean, it was published in a database conference, right? So that's the reason to compare to a database.
So, and the other, so this one is a question. So the numbers that you reported, do you report in every case also the optimization time?
I have a slide on optimization time. Yeah, we can talk about the.
We can talk about it.
Okay.
Now. Thank you.
I'll say the optimization time is high, like rivaling the cost of running it once or running it 10 times. But you can, with the degree sequence bounds, you can use the statistics and calculate, the next time you have a new kernel, calculate if any of your statistics are close. Right, so that's a little bit of a like, have I optimized for this kind of thing before? And so that's the system that we actually are using in practice with the PyData sparse implementation.
Yeah. Thank you.
But I have a question about the cost model, and because I saw that actually most of this code generation relies on the cost model. One of the challenges that we often have in the sparse code is the modeling a special locality. I think, well, for temporal and number of flops, we typically use that, and that gives a rough estimate. But always in practice, when the matrices become large, the special locality, and if you run it in the context of an application, that becomes even more challenging. So how would you, have you faced such challenges, or how would you address that if you saw them?
Yeah, I mean, that's a great question. We don't currently implement like cache blocking for our sparse code just yet. So it's not something that we're taking into account. But I think it's a fascinating problem to model. You're right that like one challenge with it is that we don't necessarily know if the non-zeros are clustered or not with the particular estimator that we used. We only know roughly how many of them there are And so we would need a different estimator if we wanted to take into account like locality in that way.
I see. So basically, the architecture and how the prefetching happens, especially for these data structures that we are dealing, like a continuous storage of non-zero elements, like they behave totally in different ways, especially when it comes to code specialization, because depends on how you do that. Then we have this non-contiguous access in some parts to actually improve temporal locality. So that actually were some of the challenges that we were facing during code specialization. That's why I raised the spatial locality discussion. But yeah, I agree, that's a very challenging thing.
Yeah, it's something that maybe that's interesting future work to take into account. Thanks for your question.
Yeah, sure.
One thing I will say is you can model certain types of spatial locality with, for example, blocking and tiling. And we do plan to support blocking and tiling. I mean, we're close. Or is it already implemented maybe?
We don't have that currently supported.
Yeah.
But
so we're close, and if blocking and tiling solves your problem, or you have, for example, regularly sized blocks, that could be supported, and that would be modeled correctly.
Okay. Any other questions right now? Otherwise, I have one for Matthias and Himir. So I think maybe a bit of a nitty question. So you guys made a big deal of the this unified array library, the array interface support for these libraries. But I think the more you spend an effort talking about these things, then it is also more annoying than when you go break the API to add your sparsity things, right? Like it seems like if you're putting so much effort into this array interface, then you still have to modify the code after that to add in the sparsity. So kind of what is the justification or reasoning about this kind of thing?
Maybe I can take that one. So if you look at the operations that are performed on a dense or a sparse array, the set of operations is very similar. The only few operations that where we have to, absolutely have to break the interface are two. One is when you're converting something into a sparse array, or somehow importing a sparse array. That one we do have to specify the format or otherwise recognize the format and import it correctly. And the second one is when you're exchanging things between libraries or exporting to another library. For that, there is a dense counterpart called dlpack that does in-memory dense array interchange. And we use that to exchange the constituent arrays in our case.
I think there was a third, right? This either extracting the code into this kernel that's being compiled with Finch, or you kind of expose this lazy nature of some of these sparse arrays in the middle of the computation. Or remember those code snippets correctly.
We do need to expose the lazy nature, but that is not something that is unique to sparsity. That is happening as well in PyTorch and in JAX. The laziness, not the sparsity, the laziness. But it is happening both in Sparse and in JAX, and we can reuse much of the same interfaces and take inspiration to copy from those. It isn't specified in the array API yet what a lazy interface looks like, but we can draw from inspiration, and there is a desire to converge on one interface.
So I can second that. So basically what breaks or is outside of array API, as we saw, was the conversion to lazy formats and running the compute, so those minimal code changes. But the main part, I think that in our cases, it's same as the array API for dense computation, so like it's not really breaking it.
Okay.
Question for Emilian. For the code specialization that you are using, that was actually interesting that you are describing it using some sort of a polyhedral notation. But have you ever explored the code size during code specialization? How does that affect the performance? And if you have ever investigated on GPUs as well, like the same issue?
So currently we're not doing GPUs.
the question was for Emilian.
Yeah, thank you for the question. So we didn't go super far on this. There's some ablations in the paper. What we can see is that we can start breaking the shapes into quite some complex bits before having concrete performance issues, given the benefits we get from it anyway. But definitely you will face some sparsity patterns, very strange ones, where this will be a bad idea and explode that we know. So it's not completely explored yet. We just know that there's a lot of cases where it will help. I don't know if this is a good enough answer yet.
So maybe how big are the codes that are generated in a struct in your code generator? Like in terms of line of code, is it like a fit? Does it fit into the L1 instruction cache or?
Yeah, we didn't have any instruction cache issues. We don't do lines of code anymore too. We do with the more like IA generation style. Yeah. In terms of lines of code itself, it would not explode that much. It's the big complexities about those indexing functions that can get quite complex in cases. But what we've observed is that it's summarized by the fact that it's just computation and no memory exchanges anymore.
I see. Okay, I think that's because you are dealing mostly with the structure sparsity that you can model it in using a compact code. Okay, thanks.
Yeah.
I guess I have a. Oh, do you have a question?
Question for Emilian.
Yeah, please go ahead.
Emilian, I was wondering I was just curious to hear more of your thoughts on how your structured tensor code generation can interact with sparse tensor formats. That sounds really interesting to me. And maybe it gets a little bit to what Kazem was asking about code size, but also just I'm curious to hear your thoughts on that direction.
Yeah, I'm glad you're interested. This is very fuzzy yet, but since you mentioned the notion of leading and following indexing, our approach really couples the iteration to the indexing if you want some performance. Otherwise, we will pay some runtime overheads to double check that we are indexing the right things. But we can avoid this lookup if we lead the iteration, basically. So I think, yeah, the first approach could be oriented this way, where we iterate over the structure part and have a following indexing on a more sparse one. For the iteration space, that might be more fun to have, I guess, to solve it generically. But yeah, it's the first thought I had.
Thanks.
Okay. Any more questions? Otherwise, we can thank the speakers. Break? Yeah, break and then one more session after this.
we can gradually start. So our first talk in this session is hyperreal specification for continuous sparse data computation with Vladimir Gladestein. Please go ahead.
Yeah, hi everyone. Well, with a talk with a lengthy title, but what we're actually trying to do is simply verify these sparse data computations, not only sparse, also maybe some matrices which has repeated values and can be compressed, and yeah, so on and so forth. So more specifically, let me try to explain you what exactly do we want to verify. So imagine you have your data, which is like somehow structured vector matrix or tensor, and you compress it somehow, so such that you also have a operation, usually written, I guess, here as a Einstein notation, which you want to perform. So the kind of problem that we tackle here is how do we verify that given this efficient computation on the compressed data, it exactly implements the pure operation on the decompressed counterpart. So to tackle this, we develop a verification framework which allows for concise specifications, succinct proofs, and accommodates general structured data types like sparse, repeated values, and so on and so forth. And also in the end, I will briefly tell you about our current work. So we are working on generalizing our framework to also handle continuous data structures. Yeah, so let's begin. Yeah, here we present the framework called LGTM, which stands for Logic for Graceful Dense Manipulation. This is the outline, and first I will tell you how do specifications look like in our work. Then I will show you a small proof outline, and finally we will talk about our current work a bit in the end. Okay, we will look at the very simple kernel, which is the dot product of a compressed vector and a dense vector. You can see the sparse vector here, and we will compress it with two arrays, xval and xint, right? So xint stores the indices of non-zero elements, and xval stores those non-zero elements. And then if you want to take a dot product, it's very easy, right? We just iterate through elements of the sparse compressed array, multiply them by the correspondent elements in dense array V, and then sum up everything together. So here is the very simple loop implementing this algorithm, and the same thing can be written using the mathematical notation, right? Well, the main question when you want to verify such computations would be how to represent formats in the proof. And the traditional approach would be to come up with specific memory layout predicates. For example, if we talk about the dense vector, usually all such kind of program logics, they have a predicate which says that, well, basically we have some pointer v, and it points to an array which payload of which is some pure sequence. And then to represent sparse compressed data, you actually will have to come up with some ad hoc predicate which says that, well, there is kind of decompressed pure sequence, and it is represented in the memory with xint, xval arrays. Once you've done this, you can, in your post condition, you can say that, well, after I run my function, I get a pointer, and this pointer points to the result written as the pure mathematical notation. So this approach was taken by the LA proof framework, and they verified the product of a CSR matrix and a dense vector. Well, that's how the representation predicate looks like for CSR matrix, and of course you need to understand separation logic pretty well to even like read it. And also it follows by hundreds lines of format specific lemmas, which I needed to manipulate with this predicate. Well, which is fine, I guess, if you want to verify like one or two algorithms, but if we want to find a
more general approach, it would be nice to have like a simpler way to represent formats. Well, so what we do in our work, we realize that actually in some works and some libraries for sparse data, people represent those formats as code. For example, like in Finch, there is a special DSL which is to represent formats. And in general, you can implement just getter procedures, getter functions, which retrieve the value at the given index in a very simple linear search fashion. So those functions kind of tell you how does the format work, and you can actually use them to prove things. So I think everyone understands here how this function works, so I can skip it. And that was the first idea of our work. How about we try to represent formats as code? But then the question is, okay, how to actually prove anything about computations now if we represent formats as code. So to give you kind of understanding of the intuition behind our approach, let's briefly look at a more complicated example, which is the dot product of two compressed vectors. So here is basically the same code duplicated twice, which is the getter function for a compressed sparse vector. And if you want to implement dot product in the two-finger merge style, the code will look like this. So it doesn't so you don't really have to understand what exactly is going on, but the idea is that you can see that the code for the dot product kind of incorporates some parts of the code of like for getters, right? Because basically the loop in this merge is in a sense a fusion of these two loops, right? Well, so our idea was to use a relational approach. So basically facilitate proofs by means of relating similar parts of the code and symbolically executing them in a lockstep. Well, now having all this in mind, let me explain you how we specify computations in our logic. So that was the old specification, and now we got rid of the predicate, but we still need to ensure that arrays, the encoding of the sparse array are somewhere located in the memories. That's why we leave them in our precondition. We abbreviate all of this as Rs. It's not super important. And now remember, we want to represent formats as code, right? So we'll have to go to the code section of the triple. And now, well, look at those xi's. Now they are not specified. So this is just components of the decompressed counterpart of our vector. And this summation mentions all of them, right, from 0 up to n-1. Of course, the majority of them are going to be 0, but we still have to specify them. So if we want to capture all of them, we'll have to run our getters on all indices from 0 up to n-1. And now it goes here. So now that's kind of how the triple look like. We will simplify it later, but for now, let me explain what does this triple even mean. First of all, this is a hyper safety specification because it relates properties of many programs. And now the idea is that we have these many runs of different programs and we run them independently. And when I say that we run them independently, that means that we run them on distinct memory heaps. So all those like heaps are equal. They assert the same predicate, but we just have different index for them. Now each getter will give you some element of your decompressed vector. And we bind all those results here to these variables x0 up to xn-1. And then we can use them in the post condition to specify our vector. All right. One thing you can notice is that the size of the triple is n+1. The arity of the triple is n+1, where n is the size of our input data, which means that n is a parameter. And LGTM is the first hyperlogic which deals with parameterized triples. So we had to develop a bunch of reasoning principles to facilitate our proofs. And now let me actually show you how roughly those proofs look like. Well, but before we even get there we will simplify, we will do some notation for this triple to make it less hairy. So instead of writing all these getters one by one, we will just collapse them into a single line with this symbolic index I, which goes from 0 up to n minus 1. And now it looks a little bit nicer, I guess. Also, instead of specifying that this predicate R's holds for each copy of the memory heap, we just have this notation to assume that it holds everywhere. And we bundle all the outputs into vector x, which we use in postcondition to specify our pure vector. Well, the first step in the proof would be to get rid of all getters which correspond to 0 values in our vector. So to do this, we introduce a special rule in our logic, which is called focus rule. And we first split this set of getters into two. First one are those getters which we run inside x in the array, right, non-zero ones. And the second one are 0 ones. So we know we can basically kind of symbolically execute those getters and get 0. So that means that we will take this part of the summation which sums all this, like sums up all this value outside of x in the array and just replace it with 0. So our focus rule allows us to focus only on those components, only on those getters which we run inside x in the array. Now to proceed with the proof, we will have to remember that our algorithm is basically a for loop. And you can unroll it, and you will see that basically you iterate over elements of x in the array. So in the same way as you run your getters now only on elements from x in the array. Moreover, the ith iteration of the loop handles exactly the ith run of this getter. So we can bundle them together, and our logic has a rule which allows us to reduce the following goal to the simpler one, where you have to just prove that the pointer which accumulates your result will, after running one iteration and one getter, will increase by one element of the dot product. And this is the just a relational logic triple. It relates to programs, so you can prove it using standard relational logic techniques. All right. Now let me tell you about our current work. So sometimes you also want to work with kind of continuous data structures, right? So there is this extension of the Finch compiler to handle this. For example, you can have images, but such that it can be split into rectangles with the constant color. And one thing you want to do is to compute the average color in a unit segment, which is called interpolation. And well, you can represent this mathematically as double integration over the function which returns you a color. And well, you might want to verify such function. So to do this in our logic, you can still implement a getter using the same linear search. So this is not much different from sparse array and sparse matrices. And then our triples look like this. So the only difference is that instead of having this like line with symbolic index which iterates through finite number of indices, now it iterates through infinite number of indices through all the real numbers. So we had to kind of adapt our logic to well, have like all the reasoning principles to handle such scenarios. And this is like the ongoing work which we hope to release very soon. Yeah, now let's talk about evaluation. So we implemented and embedded all of that into Lean True Improver. So we wanted to see if those proofs actually are short and how do they compare to non-relational approaches. Well, this is our evaluation for our previous work, where we basically verified a bunch of discrete data structures like CSR, run lengths, formats, and so on and so forth. So the average proof code size ratio was just 2.55, which is quite good in the world of formal verification. Moreover, if you compare it to unary approaches, so we also verified the CSR matrix product with a dense vector, and our proof was just 36 lines of code, which is more than 10 times shorter than the unary Hoare logic approach. And also we have slightly less extensive experiments for our continuous extension. Here the proof cut ratio is slightly bigger because you have to deal with all these continuous operations like integrations and stuff, but still I think quite good. Yeah, I think that's it. So to sum up, I wanted to show you that you can use hypersafety logics to specify computations on sparse data. You can use parametricity to streamline proofs about loops, and finally we reach up to 10x reduction in proof sizes compared to unary approaches. Thank you.
So we're going to have the question after. The next talk is quantum simulation with the sparse tensors by Meysam Tarabkha.
Okay. Hi everyone. Thank you for the introduction. It's been a pleasure for me to be here and talk about the work we have recently published in CGO'25. As the title suggests, in this work we leverage the sparsity available in quantum simulations, and we focus on using an intermediate language to develop a compiler to generate an optimized quantum simulator. More specifically, we focus on the quantum gates, and we take the high-level linear algebra behind the quantum simulation for each quantum gate, and we try to translate this high-level linear algebra to optimize low-level code. Throughout this talk, I will briefly go over the basics of quantum simulation and show how these simulations can be done by highly structured and sparse matrix vector multiplications. Then I will show how we can improve the performance of these simulations by capturing this structure and sparsity in the matrices. And I will speak about the required optimizations, and I will show that how hard it could be if we want to handle these optimizations manually. At the end, I will present our approach to address these issues, which is, as I mentioned, using an intermediate language to translate the high-level linear algebra to an optimized low-level code. And at the end, I will wrap up the talk with some of the results that demonstrate the improvements our approach had in terms of performance, maintainability, and extensibility. Let's talk about quantum computing and quantum simulation. Quantum computing, as you may already know, is a very hot topic because quantum computers can handle problems including high amount of information, and they can process them much, much easier and faster than classical computers, where classical computers are even either too slow or even unable to handle the problem. It has use in several areas like cryptography, optimization, machine learning, material science, and chemical reactions. On the other hand, we have quantum simulations. Why it's important? Because it's acting as a bridge between quantum computing and classical computing. At the moment, quantum computers are in developing stage. They are not fully developed. They are limited in the number of physical available qubits. They are very noisy, so even most of these available qubits are used to correct the noise available in these systems. So we can, at this stage, we can use quantum simulation to test the quantum approach, the quantum algorithms, validate them, use as a training tools for people, because the quantum computers, even the available ones, are not easily approachable by everyone, but the personal computer is more accessible and we can do the quantum simulation. What are the differences between quantum and classical computing? Similar to classical computing, we need to store data in quantum computing. But instead of a classical bit, which can be represented by a scalar value and can store a 0 or 1 value, in quantum computing we deal with quantum bits, or qubits for short. Here, qubits can be presented by vectors instead of scalars. For example, these are the state vectors, the 0 state vector on the left and 1 state vector on the right. One important feature in quantum computing is that not only a qubit can have a 0 or 1 value, it can have both values at the same time, which is called superposition. If we have more than one qubit in our system, we simply can do the conical product of their state vector to achieve the state vector of the overall system. For example, at the bottom, we can see the state vector of a 2-qubit circuit, where the first qubit is in the state 0 and the second qubit is in the state 1. In order to modify the state of a qubit, we need some operators, which is called quantum gates, and can simply be represented by complex matrices. To calculate the output state of a qubit after the application of the quantum gate, we simply multiply the matrix of that quantum gate to the initial state vector to calculate the output. This is very straightforward and simple algebra. We can use any tools we prefer to implement such a calculation. For example, we can use NumPy. But in real-world circuits where we have several qubits, this problem is far more challenging. Not only the simulation times increases exponentially by adding new qubits to the system, we cannot even go further than few qubits using this simple approach in a normal personal computer because of the memory limitations we have. But this is not the end of the world. We have specific tools to address these problems. For example, we have simulators like Quest, which can easily handle such problems, and we can use several qubits in the circuits to simulate the circuit. To understand how these specialized tools work, let's have a closer look to the linear algebra behind this quantum simulation. Consider a 3-qubit circuit, a very simple circuit with 3 qubits here, which we only have 1 qubit, a single qubit in this case, applied to the second qubit. The other 2 qubits should retain their initial state vector because no gates are applied on them. This is equivalent to having identity matrices applied to them, or identity gates. In order to compute the output state vector of this system, we need to construct a bigger matrix here, which we call overall transformation matrix, or OTM for short. The algebra again is simple. We simply do the conical product over the matrix applied to each qubit to calculate the OTM, and then multiply the OTM with the initial state vector. For example, in this case, if we assume the primary gate is a Hadamard gate, this on the right-hand side, we can see the overall transformation matrix we can construct for this circuit. In general, for an n-qubit system, we are looking at a complex matrix of size 2 to the power of n by 2 to the power of n. And this is where we have the issue of using general tools like NumPy here. But if we look at the OTM matrix, we can see that, okay, it's highly sparse, and even more importantly, the sparsity has nice structure, which is dominated by the conical product of the identity matrices on the left and on the right-hand side. Each of these matrices repeat the values of the primary matrix in different ways. Okay, so far we have a sparse matrix, and we want to multiply it with a vector, which I can say it's normally dense in most of the quantum simulations, and we can use sparse tools to handle this. We can overcome the memory limitations, but it wouldn't have the best performance because we still rely on the size of the matrix or the vector. But the way the specialized tools like Quest handle these problems is that they do not even construct the OTM matrix at all. Here, they calculate some indexes, which are the indexes of the elements on the state vector which we need to update at each iteration. And they use those indices to directly modify those elements in the state vector without constructing the OTM matrix. And this is how we can achieve such a good performance in these specialized tools. But there is another side to be considered here, which is the maintainability side of the problem and the solution. What I have showed in this slide and the previous slide is a sample function implemented by the Quest to simulate the Hadamard gate in this example. This is for the CPU version of their implementations. They have implemented similar functions for the remaining quantum gates, like CNOT gate, and etc. Swap gates, etc., etc. But they have a limitation, so they have limited only to the commonly used quantum gates, and they have some generic implementations to implement the remaining quantum gates if somebody needs. But as I said, this is only for the CPU version. They have implemented similar functions for the GPU version. So this approach, although has a very, very good performance, it suffers from the maintainability issues. If they want to support a new backend, they have to re-implement all the functions or the similar ones for the new backend. If they want to add a new optimization, if they want to change the data layout, they have to manually do all the things from scratch. So, what other approaches are possible? As mentioned, Quest has a very good performance, but it has maintainability issues. On the other hand, we have other specific tools like Qiskit, which, due to the huge community behind it, has a better maintainability compared to the Quest. Or we have approaches like Catalyst from PennyLane, which they have used compilers and intermediate language to support the new backends much easier than what has happened in Quest. But first, they don't have the best performance, such as Quest. Second, they still rely on manual implementations of quantum gates in their low-level code. To address this, we have introduced LFQS, which combines both features, both the performance and maintainability here. The high-level idea of LFQS is to take the linear algebra, translate it to optimized low-level code. How we can do this? We have implemented a two-stage approach for this. As I said, we are using an intermediate language, in our case, STQL. We translate the linear algebra to the STQL and feed it to our compiler as the naive representation of this algebra. Our compiler, through several optimization stages, optimized this naive expression. And at the end, the optimized expression is fed to the code generator, which generates which translates this expression from the intermediate language to the desired backend. Currently, we are supporting both CPU and GPU versions. For the CPU, we generate parallel C code, and for the GPU version as well. First stage, as I said, is the compiler version. This is the unoptimized or naive expression. Each of these green keywords are corresponded to several lines of code. And as we can see, there are several intermediate matrices. As I said, we can remove these intermediate matrices to overcome the memory limitations. On the other hand, it has several steps of calculations which can be merged together to improve the performance. The goal is to achieve an optimized expression like this, which is then fed to the second pass, which is our code generator. As mentioned, for the CPU version, we are producing parallel C code. Each of the expressions in STQL have an equivalent structure in C. For example, let bindings are translated to variable definitions, or some expressions are translated to for loops. And at the side, we are generating required syntax or commands for the parallel execution as well. One of the strengths of our approach is that if we want to handle a new backend, we can still use the optimized expression shown on the left-hand side and just do the new code generation. For example, this is the GPU version generated from the same expression. Now I'm going through the performance, and I guess I'm running out of time here. This is the performance for the CPU version, which we have compared the performance over several real quantum circuits with 26 qubits in each circuit. The closest competitor is Quest, which we outperform it by approximately 3.5 times being faster. For the GPU version, again, we are faster than Quest, almost 1.6 times faster. On the maintainability side, we have considered several scenarios, adding a new quantum gate to the circuit. Quest requires roughly 40 to 50 lines of code to be implemented for a new quantum gate, but we do handle it with just one line of code where we define the gate matrix. Changing the data layout, again, for the available gates in Quest, they need to modify around 130 lines of code, which we handle with 5 lines of code. For supporting a new backend, they have implemented more than 500 lines of code, which we handle with 90 lines of code. And yeah, if you need more information, you can go to the paper with more detail on the implementation.
Thank you for the talk. Our third speaker is Gohao Dai. I hope I'm not pronouncing it wrong. Sparse computing drives energy efficient computation for artificial intelligence.
Take that off. Okay. Okay, so very glad to be here and to be the last speaker today to present our work on sparse computing. I'm Guohao Dai from Shanghai Jiao Tong University, and currently I'm also the co-founder of a startup for AI infrastructure in China. So today I'm very glad to share some representative works in our group in the past few years on sparse computing. So let me first introduce myself. I graduated from Tsinghua University at 2019, and when I was PhD student, I'm working on the graph processing. So there's a kind of data structure which is sparse. And when I was a postdoc, I'm considering about how to apply the sparse computing into some neural network architecture research and also some AI applications.
so I'm working on some graph neural network acceleration. And now I'm an associate professor in Shanghai University. I'm working on both Sparse architecture design, something like the hardware design, and also the Sparse system designs for the artificial intelligence. So let me first go through the background of my research. As we can see that because we are providing the computing resource for the upper algorithms like artificial intelligence algorithms, so I need to look into the trend of artificial intelligence. So as we can see here, in the past 5 years, AI computing demand has increased by 4 to 5 orders of magnitude, but as a computing supply for the AI applications, the chip performance growth has slowed down a lot. So there is a huge gap between the demand and the supply, between the algorithm and the chip. That's the challenge we need to face. And currently we are moved from the AI 1.0 era to the AI 2.0 era. So what are two eras? What's the difference? For the AI 1.0 era, there are a lot of different algorithms for different kinds of applications. For example, we have convolution neural networks for the for the vision tasks, and we also have other neural networks for different kinds of tasks. So the algorithm is different for different applications. But now we are moving to the large language model era, that's AI 2.0. The difference is here that we can use one large model that is called the foundation model for different kinds of applications. We can use transformer to process vision, to process audio, video. We will show a lot of examples in the future slides. So the difference lies in the algorithm. We use different algorithms for different applications in the first era, and now we can use one algorithm for different kinds of applications. That's the difference. And to fully understand the difference, we do a lot of survey on the system and also the accelerator performance for these two eras. As you can see on the left, that is for the AI 1.0 era, and on the right is for the AI 2.0 era. And we also did a lot of survey on different kinds of performance for the system and chips. You can see for the x-axis, that represents the power for a system of a chip. But for the y-axis, that's the difference. For the first era, the y-axis is the throughput. That means how many operations can be processed on the chip or the system. But for the AI 2.0 era, the y-axis becomes how many tokens can be processed under the same constraints. So that's the difference. That's the difference. So the optimization targets for those two different eras is different. So we will show the difference in our slides. So let's first look into the sparse computing in the first era. In the AI 1.0 era, typical networks like convolution neural networks and transformers can be abstracted using a lot of different matrix multiplications and can be mapped onto hardware for execution. So if we can leveraging the sparse computing in the matrix multiplication, we can reduce the total computing and also the memory access demand for the operations. For example, you can see here on the roofline model, we can improve the equivalent computing power and computing capacity for the hardware using the sparse computing. So we can see a lot of work has working on using the sparse computing for the system and also the hardware. And typically we can use sparsity for activation and also for ways to reduce the data transfer and also the computation requirements. So let me first introduce our work on the sparse operators for the first error. This is work we have done when I was a postdoc in Tsinghua University, working on the sparse matrix multiplications on GPU for different kinds of inputs, that is input dynamics. So in the AI 1.0 era, models such as convolution networks and MLP and others will use weight sparsity that is using the pruning operations to reduce the total operations for the matrix multiplications. And some applications, for example, the point clouds and the graph neural networks will use the sparse matrix multiplication to process the inputs. So the sparse matrix multiplication is the key operator in the computation, especially for the first error in the AI. But the challenge is very huge, as we have also mentioned in previous slides and previous talk. The different kinds of input, especially the different inputs, different formats, and also different kinds of data access pattern, will lead to different performance on the same configuration. That's why we need the compilation tools. So here we show a typical example. Here we use different APIs and different configurations from the NVIDIA cuSparse library to process the matrix multiplications on the different configurations. And also here we measure the performance of different APIs and different configurations for different data sets and normalize the performance to the performance with to the APIs with the best performance for each data. So if we have one API or one solutions for different kinds of inputs, the result should be 100%. That means we will achieve the best performance for different inputs, but the result is not that good. We find that not one API can achieve the best performance for different inputs. And even on different configurations, the best API is different. So that means we cannot use one API or one solution for different inputs to get the best performance. So that's a problem. So how to solve these problems? We formulate the algorithm space for the sparse matrix multiplications. For example, I only take the sparse matrix multiplication as a very simple example, and we can see that the sparse matrix multiplications can be formulated using 3 loops. The outer loop for the to traverse each row of the sparse matrix, and the inner loop to traverse all elements. So that's here. So let me take the outer loop as an example. Because we have a lot of threads on GPUs, so how to assign the workload to different GPUs, that's the problem. So we have 2 typical implementations for here. The first one is we assign each row to one thread. So that's the first implementation. And the second one is we assign same elements to different threads. That's 2 typical implementations. And these 2 implementations will lead to different performance. For example, if each row is balanced, we will not suffer from the unbalanced problem. We will not suffer from the unbalanced problem here, right? But if each row is unbalanced, we will suffer from the synchronization overhead from the first. Okay, looks good. Okay, so I mean here, different implementations will lead to different performance on the different input dynamics. So for each loop, we find that we have different kinds of inputs, and each input will lead to different performance. So we will formulate we will get different implementations for the sparse matrix multiplication on GPUs. So how can we choose the implementation with the best performance? How can we do that? So here we train a very simple model to dynamically and heuristically choose the API, because we can get the performance prediction with some statistic inputs here. So here we train a model, And this model will dynamically choose the API, the solution with the best performance here. And follow this idea, we implement a lot of GPU kernels for the sparse processing on GPUs using different kinds of optimization, like the call screen optimization, input dynamics, and also some efficient reduction algorithms. And if you are interested in it, you can scan the QR code for the whole project. And here is the performance. We integrate our design into some graph neural network frameworks and also some sparse matrix multiplication libraries. Here we compare our performance with some commercial software solutions. Here should be DGL for graph neural network processing, and we compare some solutions with NVIDIA commercial kernels. We can achieve the performance speed up compared with them. And now we move on to the second era for AI, the foundation model era. Before I introduce our design, let me first introduce what is a large language model, what is the foundation model. The foundation model uses a transformer architecture to autographically generate the output that is a token. So the typical operations here are consisted of two parts. The first one is attention or multi-head attention, and the second one is FFN, that is a dense matrix multiplication. And we also find that there are different kinds of the foundation model. The first one is large language model, and the second one is we use the large transformer for the video or the image generation. So the roofline model for these two kinds of models are different. For the first one, it is the first large language model, it is memory bounded, and the second one is computation bounded. So how to optimize these two kinds, that's the difference. So the very simple idea for us is if we can apply the sparse matrix multiplication or the sparse pruning for the large language model, we can reduce the total computation overhead. But the problem is very huge here. The problem is we cannot bear the performance degradation for the accuracy. So there is a very different consideration between the researcher in the algorithm domain and the researcher in the circuits or architecture domain. For the researcher in the algorithm domain, they say, hey, we do not want any constraints for the specification or the pruning, right? So they want the unstructured sparsity. But for the people like me working on the circuits architecture domain, we say, hey, we do need structure sparsity because the overhead for the system or the circuits is very, very low. So how can we combine these two perspectives? We point out that we can combine these two perspectives together because for the algorithm guy, they only look into the call screen sparsity. That means the whole matrix should be unstructured rather than a tiled matrix should be structured. But for the circuits guy, they say we only need very small matrix for structure. So can we use different small structured sparse matrix to formulate a very huge the whole unstructured matrix? That's our idea. So follow this idea, we publish a paper working on the large language model acceleration for inference on FPGA for the demonstration. So follow this idea, we ensure the structure sparsity of the flexible structure sparsity for the attention and also the linear parts. And also we apply this design onto the DSP chain on FPGAs. That's something about the hardware. And we also use some fusion kernels or fusion operations to reduce the optional memory access based on our sparsity pattern. And here you can see, using this idea, we can accelerate the large language model inference with the sparsity. Here we compare our FPGA design. It is a very I mean the price and the process for this is very low. You can see it is 16 nanometers compared with GPUs. But the energy efficiency, the quality efficiency, and the throughput is better than GPU. That's the sparsity bring us. And now we come to the video generation. It is another very popular algorithms in the past and this year. For video generation, the difference is the problem becomes computation boundaries rather than the memory access boundaries. So how can we reduce the total computation? So I remember when I was an undergraduate student, research on video is already very popular at that time. So many well-known techniques have been proposed in that domain and compress the total size of videos at least 1,000 times. So that means we do not need to propose very new ideas. We can stand on the shoulders of the giants. So how can we do this? The idea is very simple. The insight is here because we can reduce the total computation overhead by explore the similarity between the videos. That has already proved to be true in the video compression domain. Okay, so we propose our hardware design for the video generation based on this very simple insight. And this paper was published in this year at PLDI'25 conference and win the best paper awards. So we apply this idea here. We explore the similarity inside the frame and also intra the frame. So that's a similarity here. We use some flag or some flag frame here to represent the similarity, and we do calculate the similarity on the fly. And we also combine our specification design with the quantization design together to fully utilize the hardware resources. And as mentioned previously, we also know that the specification will leave some workload on balance. So we also propose our adaptive scheduling to handle these problems. So that's a huge problem will be bring by the sparsity, and the online scheduling will solve these problems. We can see here is a result. We compare our design with some state-of-the-art design, and you can see from the metric, we do not lead to very huge, we only lead tiny accuracy loss, but we can see here, compared with the original video generation, our design will lead to similar results, because for the video generation, we do not need that exactly the same accuracy, but the similar video generation quality, that's enough. So you can see here, compared with GPU's peak performance or the throughput for the hardware is nearly 20 times lower from our hardware perspective, but by applying our specification, quantization, and scheduling after specification, apply 3 techniques, we will improve the performance by about 27 times. That means the end-to-end performance will be 13% higher, even with very low computation capability FPGAs. So we can improve the video generation speeds if we can turn all the design into ASIC and integrate them into the system. So here comes to the summary. Today I introduced 3 typical papers of ours for the graph neural network acceleration, large language model, and model with multimodality. And the key insight behind all these designs is similar. We want to improve the equivalent computation capability for the algorithm. That means the algorithm skyrockets every year, but the chip is not that fast. So how can we fully utilize the hardware to support the algorithms? We use some GPUs or FPGAs with lower computation capabilities, but the end-to-end performance is much more better. And I also want to say that the sparsity is not only leading to a better efficiency, but leading to a better intelligence. You can see here is AlphaFold and also the DeepSeek, which is very popular this year. They all use sparsity to get a better model rather than get a model with a better efficiency. So that means the sparsity is nature in the real world problems. So how can we fully utilize this? How can we fully understand this? That's very important for the future AI. So that's all about this talk. And my group is working on the sparse computation for a long year. So if you want to get some contact, we can discuss through this website. Thank you.
So we have the panel. I think we need just one extra chair. Check in. So we have about 10 minutes. Is there any question? Rohan?
Question for Vladimir. So I remember correctly, the proofs you were generating were very compact. They looked very short. I was wondering, what's your intuition about like compiler like generating a proof along with some of the code that it is generating? If when you get very short like this, you start to wonder, can the compiler have done that with it? So do you think we're close to doing that, or is the kind of reasoning that you're doing something that's sort of very specific to each problem, or is it something more generalized?
Yeah, thank you very much for the question. That was the original goal of the framework, and I think it's still possible. It requires like a lot of engineering though, because all these compilers, they have a lot of implementations that basically is like a set of rules which you will have to verify in your Ethereum prover advanced and then apply them. So I feel like this is possible, but given that like all these compilers have like lots of bells and whistles, it's just like some amount of engineering work. But the whole idea and the whole motivation for all these frameworks was exactly to basically produce, use them as the logic backends for such compilers, right? So produce these certifications along with the generations, yeah.
Thank you. Any other question? So one question for Guo. You at some point discussed the nature of these machine learning models becomes compute bound when you are dealing with videos. So, I mean, when you are comparing what is your baseline model, what kind of data, and why is it become compute bound?
Yeah, because the video generation model is mainly based on some diffusion transformers, and many popular and state-of-art models are using that. So if you refer to one of them, they are all compute bound, and our baseline like OpenSora and some other baselines are the sort of baselines. So you can refer to them, and they are all compute bound.
So basically all of them are using dense weight models and dense attentions,
yeah,
and all memory bound, and then when you're dealing with video and becomes compute bound.
Yeah. Most of them are based on the one kind of the transformer models called the diffusion transformer.
And is it like the RAM bound, or like are you talking when you talk about memory bound? It's just like a
compute bound. Yeah.
I see.
Is that because it's not doing like a lot of regressive stuff, or is it like, I guess I still don't get why it's not, like what is different with like text generation?
Yeah, there are two main differences. The first one is the input size for the video are much more larger compared with the text, because for the video generation, the inputs sometimes are based on the image, and the inputs will tile the image into different patch, and each pixel will turn into embedding. So compared with the text, the input is much more larger. That's the first difference. And the second one is the autographic part compared with the text generation is relatively small in the video generation part.
But if the batches are large, doesn't it make okay? I mean, depends on the computation, I guess. Okay,
Yeah.
thanks. If is there any other question? Because I have yeah, go ahead.
Do you have any insights? How about audio? So you have talked about text, you have talked about video. How about audio?
Yeah, honestly, we are not working on the audio, but from my perspective, audio is much more similar to the task, I think. So I'm not sure if it has memory bonded for the generation parts.
I see. Okay, thanks.
I have a question for Mason. So I think the discussion of converting to a sparse tensor, it still wasn't clear to me why should we tensorize that if the pattern, like you have a small matrix and you just keep repeating that. I understand well how you convert those small matrices and put them together as a one big sparse matrix, but it's not clear to me still why you should do that explicitly and not just simply working with those small matrices. I remember you were talking about just sort of a repetition somewhere.
Oh, yeah. Yeah. One main feature in quantum simulation is called entanglement. So you cannot simply if, for example, in the simple example we had, if you had 3 qubits in the system and only one quantum gate, you cannot just multiply the small quantum gate to that, in our case, second qubit's state vector and say, okay, the other ones are unchanged and we are changing the second qubit. This affects all the other elements in the state vector. So we have to generate a lot, if we are looking at the matrix vectors version, we have to generate a larger matrix which covers all the circuit. For example, if it's a 3 qubit system, we have to generate a 3 qubit quantum gate and multiply it with the state vector of the whole system, not only the second qubit.
So does it mean when you are tensorizing it, you are reusing that vector, but if you want to do it in a matrix-free form, you have to load those vectors several times? Well, does the reuse happen on the vector side when you tensorize it, or?
It changes all the elements. For example, as mentioned, having a quantum gate on the second qubit can affect the, let's put it this way. Remember how we generate the overall state vector of the system? Okay. It's the conical product of the states of each qubit. So the overall state vector is kind of entangled state of all qubits at the same time. So we cannot just simply use the small matrix here.
I see. So the effect of those qubits on each other will be reflected better.
Yeah.
You don't have to access matrices like, oh, that makes sense now. I see. Thanks. Any other question?
Yeah, I have a follow-up question. So I'm wondering, so is there any different types of sparsity in quantum simulations you have observed? Like maybe not I think maybe what you mentioned is not limited to quantum many-body problem, maybe other problem as well. So I'm just curious, like any different types of sparsity. So I know block sparsity, but I don't know the others, if they exist. Yeah.
There are 2 types of sparsity available in the quantum simulations. As I mentioned, the vector part is usually dense, apart from the very initial of the circuit. After just 1 or 2 quantum gates, the vector part is fully dense usually. but the matrix part is always sparse. The sparsity comes from two sides. The major portion of it comes from the identity matrices and the chronicle product, which are discussed in the slides. There are another small portion for the sparsity, which comes from the quantum gates themselves. Those are small matrices. I think I showed the Hadamard matrix here, which was not sparse at all. But we have quantum gates like NOT gate or C NOT gate, which themselves are sparse. And they put another layer of sparsity in the matrix, which we also cover them in our compiler and optimization paths.
So will, like, for example, diagonal format will be helpful. So for some gates, so will it be beneficial to use other different special formats for the gates, for like say NOT gates, so on?
It's not a different approach for those gates. The approach is the same. Mm-hmm. The result is different. The difference is the last stage of our optimizations in our compiler, which we take into consideration the values of the matrix itself. So before that, we have generated a generic term to update the element, which, for example, for a single qubit, it consists of 4 sums. But when we consider the gate matrix itself, for example, in a CNOT gate, maybe 3 of these summations will be removed because the values are 0, and only 1 remains in the expression.
I see. So it's kind of dealt with in the compiler itself, not from the format, right? So dealt with the computation itself. I see. Yeah. So you are going through, you take the state vector approach, right? So will it, I'm thinking about will another approach like tensor network approach will be any different? So have you explored anything about that?
No, I haven't explored that.
Yeah, just a curiosity. Thank you so much. Yeah.
Thank you.
Thank you. Any question? No?
For Guohao, what would you say the programming language or compiler need is for sparse machine learning? Or is there one? I mean, maybe there's, if you know the architecture that is sparse that you want to do, and that's the most important architecture, and there's billions of dollars for this architecture, then we can get very, very talented people to write a dedicated kernel for it. So I'm curious if you think there's any cases where we have really dynamic architectures or kernels, or there's a need for something like that, for some dynamism of the execution layer itself.
Yeah, I think it is a very good and also the open question for this era. And let me figure out some perspective. The first one, I think, is the compiler should be aware of some domain-specific architecture. For example, the tensor core, the sparse tensor core, from the hardware perspective, that is quite different from the machine learning and general computation. That's the first one. And the second one is, I think the compiler should be fully understand the sparse pattern from the machine learning algorithms. That is very different, as we have mentioned in quantum computing, and in other domains, the sparse pattern is quite different. And from my perspective, the sparse pattern in machine learning is a little bit different from the general computation. For example, the block sparse for the video generation lies in the input dynamics between of the sparsity in the video. So that's the second one. We need to understand the sparse pattern. And the third one lies in that I think there is not a whole flow for the sparse computing in the machine learning for the compilation. Currently, we have some compilers for sparse for some general computation, but now we do not have the whole flow for that. So that's a very huge engineering work for that.
Thank you.
Thank you.
Thank you. I guess we are if there is no other question, I think we are good because that's like exactly on time. Thank you for the speaker. Let's thank our speaker again.
Thanks everybody for attending the second version of the Sparse workshop, and yeah, hopefully we'll see you next year. I'm not gonna be there because it's in the US, but
Oh, is it in the US?
yeah, I think PLDI is gonna be next year. Is it? It's gonna be in the US. Yeah.
Did they announce it already?
I don't know.
I don't know.
Usually it runs like that. Yeah. No, maybe they don't know it even, but usually it's gonna be in the US. Yeah. Yeah. Okay. Thanks everybody again.